Very large IP networks, such as those defined by a /16 or /8 prefix, can result in tens of thousands of hosts being assigned to the same Layer 2 broadcast domain. In the example shown, the /16 network can support up to 65,534 hosts. While valid in terms of address space, such a large network is highly impractical from both a performance and management perspective. A single broadcast domain of this size leads to excessive broadcast traffic, collision risks, and difficulties in fault isolation and monitoring. This structure lacks scalability and is not suited to modern enterprise or service provider environments. The appropriate approach is to subnet these large address blocks into smaller, more manageable subnets, improving efficiency, security, and control within the network. To address the inefficiencies of large flat IP networks, the solution is to introduce a hierarchical structure by dividing the network into multiple subnets. Each subnet corresponds to a distinct physical network, which may be based on Ethernet, Wi-Fi, or other technologies. In this example, the larger /16 block is logically divided into smaller subnets, each connected through routers. The third byte is used as the subnet identifier, forming a structured addressing plan. This hierarchical approach improves routing efficiency, limits broadcast domains, and supports scalable network management by localizing traffic and isolating faults within subnet boundaries. In subnetting, we extend the original network prefix by allocating some bits from the host portion to define a subnet ID. This is known as the extended network prefix. For example, in a /16 network, we have 16 bits for the net ID and 16 bits for the host ID. By borrowing n bits from the host ID to use as a subnet ID, we effectively create smaller, logically separated subnets within the original network. The number of bits to allocate for the subnet ID, denoted by n, is determined by how many subnets we want to create and how large each subnet needs to be. The remaining 16 to n bits define how many hosts each subnet can support. This structure allows flexible, hierarchical IP addressing, improving scalability and efficient network segmentation. The subnetting is very much similar to the telephone numbering systems. This analogy helps illustrate how subdivision and routing work efficiently at scale. In the IP world, an IP address can be broken down into site, subnet, and host components, similar to a telephone number such as 310, 824, 2296, which includes the area code, exchange, and connection number. Each part narrows down the location. The site or area code identifies the broader region or network. The subnet or exchange narrows it to a specific internal group, and the host or connection pinpoints the exact destination. This example demonstrates how to apply subnetting to a /16 network to create at least 1,000 subnets. To achieve this, we require at least 10 bits for the subnet field, since 2 to the power of 10 is equal to 1,024 subnets. These bits are borrowed from the host ID portion. Therefore, the new net mask becomes /26, 16 original bits for the net ID plus 10 bits for subnetting. This leaves 6 bits for the host ID, allowing up to 2 to the power of 62 equal to 62 usable host addresses per subnet. We subtract 2 for the network and broadcast addresses. The binary diagram at the bottom shows how the address space is logically divided. Net ID, subnet ID, and host ID, providing a structured and scalable way to allocate IP addresses efficiently. Building on the previous example, this slide shows the actual subnet addresses generated from the initial /16 block using a /26 subnet mask. The subnet mask leaves 6 bits for the host field, allowing 62 usable host addresses per subnet. The binary representation helps visualize how the 10-bit subnet field changes with each subnet. Suppose we are allocated a /24 network, which gives us 254 usable host addresses. We need to build 3 subnets with 60 hosts each, and 2 subnets with 30 hosts each, totaling 240 hosts. If we try to use 2 bits for subnetting, we get 4 subnets, but each can support only 62 hosts. This isn't sufficient for our layout of 3 times 60 and 2 times 30. Using 3 bits yields 8 subnets of 30 hosts each, which also doesn't satisfy the 60 host requirement. Although the total number of needed hosts fits within the /24 block, classic subnetting wastes address space because all subnets must be the same size. This inefficiency raises a crucial design question. How can we divide our network more flexibly? matching subnet sizes to actual needs. This leads us to a more advanced approach, that is the variable length subnet masking, or VLSM. VLSM allows us to apply different subnet masks to different subnets based on specific size requirements. In this example, we start with a /24 block and first apply a /26 mask, which divides the block into 4 subnets of 62 usable host addresses each. To meet our design needs, we then take one of these /26 subnets and further subdivide it using a /27 mask, creating 2 additional subnets that support 30 hosts each. This hierarchical and efficient allocation of IP addresses maximizes utilization and avoids wastage, making VLSM a fundamental technique in modern IP network design.